Hi, and welcome to our section on Python's coroutines and asynchronous processing. In our previous section, we looked at using multiple processes to increase the rate of data processing in our programs, which is great for CPU-bound programs because it allows the program to use more than one CPU. In this section, we're going to look at the inverse case, using a single CPU to handle multiple data processing tasks at once within a single process, which is great for I/O-bound programs. In this video, we're going to take a moment to examine the differences between asynchronous processing and parallel processing. We will specifically look at why multi-threading is not good for servers, cooperative scheduling, and finally, end with the coroutine syntax for Python. When we were working with the concurrent.futures module in Section 6, we saw a way to make two or more streams of code run at the same time. We could create an executor object, and then, whenever we wanted to run the code in parallel, we could tell the executor to run the code. The executor would give us a future object that we could use later to get the result of the code. And it would then run the code in a separate process. Our original code kept on running in the original process. We talked about how this could improve the performance of CPU-bound programs by letting the code be divided up between multiple computer cores. But it seems like a technique that could be convenient in a lot of other circumstances. It's handy to be able to tell the computer, go do this, and let me know when you're done. One place where that ability seems particularly useful is in network server programs, where having a separate stream of execution for each connected client makes the logic and structure of the code much easier to grasp, which means it's easier to write bug-free servers when they're structured that way. There are ways to write a server that uses only a single stream of execution, but if we have a way of writing servers that probably introduces fewer bugs, why wouldn't we? The problem is resource overhead. Every process running on a computer uses up memory and CPU time, of course. But in addition to the memory and CPU time, it actually needs to run its code. The operating system also needs to expend resources to manage the process. As it happens, the time spent on switching between processes is significant. The memory overhead is enough that it becomes a limiting factor on how many clients a multiprocess server can handle simultaneously, and other internal operating system resources may be even more limiting. For CPU-bound programs, there's a sweet spot that produces optimal results, where the program has one process per CPU core. For an I/O-bound program, which most servers are, any process beyond the first are nothing but overhead. As I mentioned, there are ways to write single-process servers that can handle multiple clients at once, with much lower overhead per connected client. Using these techniques actually allows a server to handle many more clients at once than a multi-process server program could. At once, even when not operating at full capacity, a single-process server leaves more of a computer's resources available for other uses. So, on the other hand, we have a way of writing servers that is logically structured and less prone to bugs, but waste resources. On the other hand, we have a way of writing servers that is resource efficient, but easy to get wrong. Can we somehow get the best of both worlds? The answer is yes, fortunately. Python's standard asyncio module combines the low-level techniques that allow a single process to service multiple clients with a cooperative coroutine scheduler. The end result is a programming interface that looks and acts a lot like concurrent.futures, but with much lower overhead per stream of code execution. That's great, but what's a cooperative coroutine scheduler? For that matter, what's a coroutine? A coroutine is a computer science concept, a function that could be paused and resumed at certain places within it. Each time it pauses, it can send data out and each time it is resumed, it can receive data. Python programs can define coroutines using the async and await keywords, and asyncio makes extensive use of them. A cooperative coroutine scheduler is a piece of code that picks up the execution each time a coroutine pauses and decides which coroutine should get to run next. It's called a scheduler because it keeps track of multiple streams of execution and decides which one gets to run at any given time. It's called cooperative because the scheduler can't yank the right to be running away from one coroutine and give it to another. It has to wait until the running coroutine pauses itself, and then it can select another coroutine to run. In Python coroutines, the pause and resume points are the await expressions, which are also how we call other coroutines. Every time we want to perform a function, call on a coroutine from inside another coroutine, we await the coroutine we want to call. As far as the semantics of the code work that behave just like calling a function from inside a function, the other coroutine runs until it returns, and we get back the return value. That's how the code behaves. But what it actually does is quite a bit more. The first thing that happens is that the coroutine we're running is paused. The coroutine we want to call is handed off to the scheduler, which places it into its list of coroutines that need to run. Then the scheduler checks to see whether anything has happened that a coroutine was waiting for, such as new data coming in across the network or another coroutine returning. And if so, it adds the waiting coroutines to the list as well. Then the scheduler picks one of the coroutines that needs to run and unpauses it. That means that if a coroutine has a long-running loop that doesn't contain any await expressions, not only will it block any other coroutines from running, it will also keep the program from checking for new data coming in and prevent assorted other input and output operations from being serviced. If we have such a loop, and there's just no reason to call any other coroutines inside it, we can place an await asyncio sleep 0 statement into the loop body, which simply gives the scheduler a chance to do its thing. That little bit of extra complexity that comes from needing await expressions is the price of cooperative scheduling. But since the payoff is efficient and logical code for I/O-bound programs, it's often worth it. That's it for this video. In the next video, we'll look at some of the nuts and bolts of working with asyncio.